Hello everyone, I'm Max and welcome to our 14th lesson, Logarithmic Functions. I do apologize for the week and a few days of the delay for this video. I went to Japan and then I was sick and just a lot of stuff to do, but yes, after a week and a few days, we're finally here, so let's get ahead and start with the lesson. First is what we remember from the previous lesson since it's been so long. Hopefully we still remember that the exponential function is written as y is equal to a to the power of x. Why would this be important? Well, we know how to get the value of a, which is by taking the xth root of y. And to get y, we put a and multiply it to itself x times. So the only value we need to know, or the only one of these three that we still don't know how to get, is x. That's where logarithms come in. This function of sorts that gets the value of x is called a logarithm. Logarithmic functions are the inverses of exponential functions, so let's see how this would look like just in general and how to get one from another. This is the all familiar exponential function. So to get the inverse, we switch the variables. We know that y is a function of x. So let's introduce the way to write logarithms and keep x in it. So as a variable, as a function. So basically a function of x. We get something like this. But this is not entirely correct just yet. We need a. We put it here. Here is a screenshot from storyofmathematics.com, which gives us a very handy explanation of what each part is and how conversion works. We see that the base a, so here, is written in the subscript right after the log, and x, aka x, aka b, or the value or result of the exponent equation, is written in the brackets of the log function. Y, or in this case, n, the exponent, is the result. This means that the right side of the equation, so log of x with base of a, is the formula for the exponent to which a is raised to get x. This is all very confusing, so the first rule is a is greater than 0 and it's not 1, and essentially this formula is the formula for the exponent. So as basically I could put a to the power of logarithm of base a of b, and we'll see later how that works, but logarithms basically exist to answer the question, to what power must I raise a to get y, or in this case, a to get b. Here is a graphical example. We see that the exponential, red one, is indeed inverse from the logarithmic one. However, you see the base here too. If we increase this base to 10, 20, whatever, the higher the base goes, the less curved it is, and the faster it changes before reaching y equals 0, and then it slows down a lot. Like at the higher bases, I think it looks almost flat. Just like higher exponents, where the function pretty much looks like a square or a rectangle. Let's see some examples. We know that 2 to the power of 3 is 8, which means that the log of 8 with base of 2 is 3. That's just the basic conversion that we just seen. Another example is log of 1000 with base of 10. We know that putting 10 to the power of 3 will give us 1000, so the result is 3. You could also just take this number and divide it with this one until you get 1, but that's only for logarithms that give us like whole numbers or natural numbers. There will be examples. If you take the logarithm of 2 with base of 10, you already can't divide anymore, so the result will be something between 0 and 1. But we'll get to that later. Hopefully this gives us a small idea on how logarithms work. Of course, just like with roots, there are ways to approximate the value, and I think the logarithmic one is slightly easier. But before that, we need to cover the properties and a lot of other stuff. That way we actually know how this approximation works. The first thing is very important, the common basis, aka the a and the subscript. The most common two are 10 and e. They also have their own markings. Base 10 can also just be written as log of x, so 10 is omitted, and base of e can be written as ln of x, and is read as natural logarithm. The log of x is read as the common logarithm, and appears mostly in science, for instance pH levels of acids and bases, engineering, while the natural logarithm is used in calculus and growth and decay functions. But yes, the inverses are determined the same way as before, where we just replace a with either 10 or e. Here in this case we just don't write them down because they're special numbers. Well, special. Most commonly present in any math we do. So on to graphing. The graph looks something like this for a's that are greater than 1, and mirror over x-axis for all a's that are between 0 and 1. As you can see here, it's a lot more steep here, and then a lot more flat over here, because the base is higher than before. So the domain would be all positive numbers. As with these functions, y value is the exponent that the base is raised to get the x value. Meaning, since a cannot be negative, x can't be either, as positive numbers cannot become negative through exponentiation alone. Same thing for 0. There is no number that when raised to any power gives us 0 as a result, meaning our x here cannot be 0 either, giving us a vertical asymptote at x equals 0. Range is simple. Just as we can use any real numbers as the exponent to real numbers, so can our y's be any real numbers. Next up are a few very useful laws or rules for handling logarithms. They can help us simplify equations, separate variables, etc. The first rule is the product rule, which states that a logarithm of a product is equal to the sum of the logarithms of individual values, like this example shows. We have a logarithm of r times k with a base of a, but we're gonna ignore the base for now. And this is equal to logarithm of r plus logarithm of k. This also goes the other way around, so if we have two logarithms that are being added together in our equation, we can substitute them for one logarithm where both values are multiplied to each other. This is very handy when you're solving slightly more complex equations in physics or chemistry and you just have several logarithms that are added or subtracted, or even like a product within a logarithm and you can just break it apart. So yeah, if we think why this makes sense, well, each individual logarithmic term represents an exponent, whereas the value in it represents here the base and here the result. So if we had a to the power of y, which equals to r times k, like rewriting this in this form, we know that both k and r must be multiples of a, because rewriting this as such, there's no other possible factors that we could get out other if we assume that a is a prime. If a is like 4, then of course there's going to be 2's here, but let's just assume that that's how it is. Because, well, a's are present here. There's no like 4 times 4 times 2, because it's only 4 times 4 times 4, for instance. Basically, that exponent, if we separate it as at any random point, that exponent will always be lower than y. So let's cut it right here. That's 1, 2, 3, 4, 5 a's. 5 is obviously less than y in this situation. And if we cut it like this, that means that r could be written as a to the power of y2, where y2 would be 5. So we can rewrite k and r as these, and we see that when we multiply two numbers with the same base and different exponents, the exponents are added together. This is one of the rules we have already learned a while ago, but it shows here very well and explains why these rules actually work. So if you're ever stuck and you don't know how to work on, just rewrite it. There's no problem in rewriting the equation as long as you make sure that it makes sense and it's actually an equation. Because if you multiply both sides with 0, sure, it's an equation, but you've kind of lost the values. But yes, that's why you can add 3 on both sides, you can divide by 4 on both sides. Basically just make sure that the equation is the equation. It's the same thing, so if you put the equal sign between the two, it makes Actually, no, that's not how it works, but yeah, who cares? Basically just rewriting as such, and these are the rules that we already have learned, and they show here, especially here. The second rule is the quotient rule, which states the same thing about division. When we have the difference of two logarithms with the same base, we can rewrite them as one logarithm of a quotient between two values. So if you have this or this in your equation expression, you can replace it with the other one depending on your needs. Combining these two rules gives us a very handy method of approximating the value of any logarithm. We need to break the value of the logarithm into prime factors, just like we did at the start of our math chapter when we learned about primes, greatest common divisor, and so on. We do the same thing here, break into primes and add together logarithms of the same primes. All that you need now, which is probably the hardest part, is to learn the solutions. But then again, if you learn the solution for base 10 and primes 2, 3, 5, 7, maybe even 11, you're most likely going to be able to solve vast majority of examples you could come across quite fast. I think at the end of our high school we had, for maths, we had the big test at the end, and the maths one either has calculator or doesn't, and that's like those who graded decide. And if you cannot have the calculator, this is a very handy way to calculate the approximations or to just see if you're correct. But then again, I don't think this was demanded from us on our course. So, but yeah, it's a very handy trick to like just do logarithmic solutions quite fast. You will see in a bit why they're so accurate. But if you look at it, just like the golden ratio and everything, this appears in a lot of places. Like, you can logarithmize, whatever the word is, a seemingly non-linear distribution of points in a graph, and you can get a linear distribution out of it. So it's a very handy thing. It's a very common thing in, well, not everyday life, just science and calculus. But then again, you do this for fun or just to know it, so I guess it's not as important, but hey, it's one more skill to learn, and in a world without magic, might as well, you know? But yes, second rule applies. If you want to know the approximate value of, let's say, the log of 50, we could rewrite this as the log of 100 divided by 2, or the log of 25 times 2, whatever you want. I'm gonna take the first. So, log of 100 divided by 2. So, using the second rule, we get log of 100 minus log of 2. And log of 100 with base 10 is easy to know, as 10 to the power of n being 100 means n is 2. As for log of 2, it's not really intuitive. It's circa 0.301. Remembering just a few decimals is enough for approximations. I think 2 or 3 is super accurate still. And this gives us the result of 1.699, while the real value, to 2 more decimal points, but not all of them because it's irrational. The real value of the logarithm of 50 is 1.6989700043, etc. So we see that we got it correct, as an approximation, of course, within a certain margin of error. This is a very good way to eyeball the value of the logarithm. Sure, as a chemistry student, this may be handy. In just general calculus, could be handy if you're not working with calculators all the time. But for everyday life, I guess it could be useless. But yes, the next rule is the power rule. It states that when the value in the logarithm is raised to some power, so like here, that power can be moved out and multiplied to the logarithm of the unraised value. So r to the power of k under the logarithm could be written as k times the logarithm of r. This also makes sense as putting an exponent over the result of some a raised to y basically makes that a to the power of y to the power of k, and we know that when you put an exponent over an exponent, you can rewrite that as the product of both exponent. In this case, k times the logarithm, which, as we know, represents the y. Now, if we had a radical or a root over r, so like here, like the kth root of r, we would simply divide the logarithm of r with k, so just the division line and k under it, because as we know, the exponent when the number is in the denominator, that thing is basically the power of the root. I forgot the word. God damn it, I should really look up my videos. But yes, the next rule is the identity rule. It's quite useful for simplifications, and it makes sense. It's an identity. It states that when we have the same base and the same value, the result is 1, as a to 1 is a. And for our last and probably the second most important after the product and quotient rule that we will cover is the change of base. Sometimes we will have a different base in one term than the rest, which is where this is very useful in. So for it, we make a division line. Under the division line is the logarithm with the value being the old base and the new base being the new base. So here that's the log of b with base of a, as b was the old base. And then on top of the division line, we put log of the value, so the original value stays here, and then just the new desired base. If you're ever not sure how to remember it, just try to remember that both use new base, because it just makes sense because you're converting it to the new base. And just like how on the left you have the base written slightly lower and smaller than the value, you can imagine like a diagonal division line. This one is lower, so it's gonna be on the bottom, and this one is bigger, so it's gonna be on the top. Kind of makes sense. You let the bigger one stop. But of course, there's a mathematical explanation of why this is the way it is. But this falls as something more advanced, and while I'm not discouraging you from looking it up, I would be honestly proud if you got inspired enough to actually look it up and see for yourself, because that's how studying works. You find something that interests you and you pursue the knowledge yourself. But I'm not gonna put this in this video because I don't think it's as widely useful in life. I mean, logarithms aren't that common. We're using them just so we can get to future lessons and actually understand them to some point. But the explanation of why this formula is the way it is, I think you could go with exponents as well. But the explanation is not important here right now, because the formula is relatively simple, and probably with explanation I would overcomplicate it. But anyway, let's solve some examples to see how these rules or laws can be applied. For our first example, we have two ways to solve it. Either we solve logarithms first and add or multiply the values and then use the logarithms. So I'll do the latter. I'll combine them under the same logarithm. So we multiply the values inside that. We get the logarithm of 32 with a base of 2. Now, since let's say I don't know the 2 to the power of 5 is 32, let's divide 32 with 2. We divide it once, we get 16. We divide it twice, we get 8. We divide 3 times, we get 4. We divide 4 times, we get 2. 5 times is 1. So when we get to 1, we divided it 5 times with 2, which means that our result is 5. I overcomplicated this more than it needed to be. But yes, if you wanted to solve this the easier way, 2 to the power of 3 is 8. So 8 divided by 2 divided by 2 divided by 2, that's 3. 3 appearances of 2. And in the right one, you have 4 divided by 2 divided by 2. That's 2 instances of 2, so 3 plus 2 is 5. Either one was correct, of course. Our next example wants us to expand the following expression. We see that we have a division inside of a logarithm, and we have some exponents, but let's leave this for a bit later. This means that with division, of course, we can rewrite this as a difference between logarithms. So we take the top part and put it in the first term, and then take the bottom part and have it as the second term. And now we could leave this as such, but there's still more to be done. We have x raised to some power, so we can just take this power out and move it in front of the logarithm, giving us this as our final solution. And for our last example, you can solve it in a variety of ways. I could let you solve this by yourselves, but that's why we have the mini test. I will use the last rule personally, of course, for this example, because it may just be the simplest way. And I will change the base of the second logarithm to 10. I could change the first one to 100, but I can see this exponent here, I can see this here, so I know that this is gonna be much easier, so much nicer result than if I were to convert this one. So I moved the 2 at the start into the logarithm for later, so it becomes the exponent. and I changed the base according to the formula. So I used the old base as the new value in the bottom, and I used the old value as the new value with the new base. So this is how it will looked like. And now I know that the logarithm of 100 with a base of 10 is equal to 2. So I'll rewrite this as such. And since multiplication to the logarithm gives us the exponent, division gives us a radical or a root. And if we take a square root of x to the power of 4, we get x to the power of 2 because we know that even roots are not negative. So we get these two, and now we can just either add them together, either by multiplying them under the same logarithm, or by adding them to get 2 times log of this and then just putting it in to get the exponent. But our final result is logarithm of x to the power of 4 with base of 10, or just a common logarithm of x to the power of 4. Nothing too hard, as you can see. It looks more complicated than it is in reality. Next is logarithmization. I'm not sure this is even a real word, or I mean, I know it exists, I just don't know if I spelled it correctly, so there's a question mark here. I know that British people have S and Americans have Z, but that's not important for this point. Basically, this process is moving the values from exponents into the equation as constants or variables that can be individually rearranged. I know there's a lot of keywords here and it's complex, but it's probably not the right definition as well, but I guess that's how I made it make sense to me. But you'll see on the example. So we have basic logarithmization is like multiplying by a number. Well, sort of. In the example here, I would logarithmize both sides with the logarithm with a base of a. Logarithmizing the left side would give us logarithm of a to the power of x, which has the base of a, of course, because you make sure that the base stays the same as the one in with exponent. So we would carry x out, and we would have x times logarithm of a with a base of a, which we know equals 1, so we have x on left. And on the right side, we would have logarithm of y with a base of a, as it says here. I don't know why I got so confused there. Also, from now on, I'll just say log, as in I'll log this equation, to make it easier to pronounce it, just to avoid what just happened. But yes, this is known and familiar by now, and to undo this, you would just exponentialize. So this isn't the most correct word here, I guess, but basically you take the base of the logarithm and you raise that base to whatever is on the left side, and that is the left side, and then you do the same thing for the right side, so the base raised to the entire right side. And yes, you can change between the equations at will with the proper steps. What is interesting is when you have a whole equation, and you can suddenly make it much easier to choose which variable you're gonna be calculating. I will show you this one example, or one of the examples I had encountered in my chemistry course, and the equation itself does look a bit, well, very daunting, but don't worry, we will cover this one day, and that day is still a while away. My best estimation would be about 3 years. But yes, I'll simplify this so you don't have to look at so many different variables. This equation is called the Clapeyron equation, or CC equation for short. If we know the pressure and temperature of a vapor at a certain stage, we can use this to predict what happens if one or the other changes. Here we have a natural logarithm, so E is the base, and we have the logarithm of pressure at a second point divided by the pressure at first point, which then equals a certain constant, which is the delta H was the enthalpy, but that's different for each, so that's not important right now, so I'll just say it as a constant, which is then multiplied to the difference between the inverse of the temperatures, so 1 over temperature 1 minus 1 over temperature 2. But yes, why this? We will derive this when we get to it. But basically, yes, how we got this formula and why does it work, it's not important. It only matters to show us how this lesson works for us. So either use this marking or type antilog. So writing antilog is correct, or just writing exponentiation. as technically exponentiation would be antilogarithmization, so antilog for short. And in this case, we remove the logarithm on the left, and as, of course, e to the power of natural logarithm of p2 divided by p1. These two cancel out, we get p2 divided by p1, that equals e to the power of the entire right side. And this is the second form, which makes it easier for us to calculate pressure, while the first one helps us calculate the temperatures, if that's whatever we need. So yes, we use these two formulas. Usually there's like a delta in front of here that shows change, or somewhere, delta temperature. But that's a differentiation and everything. We'll get to that in 3 years when we cover this lesson. Do not worry about it all. If you don't understand the equation, there's no problem at all. Just look at how the letters move, okay? Look at the mysterious behavior of the letters. Ignore what they mean, just look how they move, okay? But yes, as you can see, the process itself is not that hard at all, despite looking complicated. I could have chosen an easier equation to do this on, but I don't know, this one just hits different, you know? You're gonna see how crazy good this equation is when we're using it. It's severely underrated. Well, this was it. Hopefully this was enough for you to solve the mini-test. If not, feel free to join my Discord, link down below. And thank you again for tuning in to my lesson. Again, mini-test is on the screen, as you can see. I wish you the best of luck solving it. And I'll see you all in 2 weeks. Just the normal schedule is continued. I do not have enough time to finish my next video in 1 week, as I'm still sick and recovering. But yes, thank you everyone for tuning in today. I love you all, and I'll see you on our next quest. Bye.